So we were discussing the response of a linear system with harmonic excitation, and in fact we were discussing the steady state response. But in fact, if you go to calculate the response, you may see that, and I told it also earlier, that the response is actually separated into two parts. One is the response due to the initial condition, that means the response without any force, and second is the response only due to force with zero initial condition. So if we start from that point, so we'll have a system, linear system, mx double dot plus kx equal to ft, and we said that the response, total response, is the response due to the initial condition. So this is x, let us say x free, and maybe x force, where this response is due to non-zero initial conditions. And this is due to force with zero initial conditions.
Sir?
Yeah.
Sir, so this solution is similar to solving a differential equation, like the answer will be sum of the homogeneous part and the particular solution.
Right, homogeneous and the particular solution, but with a difference that in this one, in the force response, we are considering the we are also considering the response where the initial condition is zero. So you say that it may not be always so if you consider the homogeneous part and the particular integral. I'll tell you that if the let us say we were solving mx double dot plus kx equal to, let us say, f naught sine omega t, the particular integral will be, you see that this will be equal to k minus m omega square sine omega t, right? This is a particular integral, and the homogeneous part will be equal to a cosine omega t omega nt minus pi. Okay, so you see that in xpt, xp at 0 equal to 0, fine, but xp dot at 0 is not equal to 0. So it's the homogeneous part. So this is the particular integral. Particular integral does not necessarily have zero initial condition. So, but what I am saying is that I am breaking this response into two parts. One is the response due to the force with zero initial condition. That means there is no initial condition. So here x, if I say force, here I have zero initial condition. So here all the x0 equal to 0 and x dot 0 equal to 0 has to be satisfied for this. And here x free, where x0 is the given initial condition x naught and x dot 0 is the given initial condition b naught. So entire initial contribution of the initial condition is taken here. The other contribution, that means the due to the force, is taken in the other part. So for a linear system, this is always possible. Okay. It is very similar to separating the response into homogeneous part, homogeneous solution, and then the particular integral, but exactly not equal to that. So there is a slight difference because in the forced response, I am not considering the effect of the initial condition. Is this clear to you?
Yes, sir.
Yeah. Okay. Now we were considering, let us say, sine omega t, or in general, we are considering e to the power I omega t, or e to the power j omega t. Okay. Knowing that the real force will be the real part of this, and we will calculate x hat, and the x will be the real part of x hat. So this preliminary discussion we had in last class, and I am now considering only the response due to the exponential type or e to the power j omega t type force. So it's a complex function. Now, as we say that, so x of x free in that case, this will be equal to a cosine omega n t minus phi. That is as usual. But what will be the x force? X force response. That means suppose there were the system were to start from zero. That means from the equilibrium point with no velocity. So there was initial velocity 0, initial displacement 0, but we are applying force, that is e to the power j omega t force is being applied. Okay. So what will be the response due to that? Okay, so you see that this response, this will be equal to F naught. You see, only the, so now actually the homogeneous part will be, let us say, a cosine omega a to the power j omega n t plus b e to the power minus j omega n t plus f naught divided by m omega n square minus omega square e to the power j omega t, such that what happens, x force, because we are considering the x force t equal to 0 is 0 and x force dot t equal to 0 is 0. So we'll have to find out a and b such a way that this condition is satisfied, because by definition this is the contribution due to the force with 0 initial condition. So for this one, actually a and phi, capital A and phi will be such that it will contain the all the information about the initial condition. But here small a and b, so these two will be selected such a way that the initial condition for x force, this becomes equal to 0. So you see that now that becomes a plus b equal to f naught divided by m omega n square by minus omega square, and and a minus let's say power, so a minus b j omega n, this one will be equal to f naught divided by m omega n square minus omega square and e to the power j omega t, so j omega this part. So velocity and displacement, this both of them will be 0. So it may not be very difficult to get the value of a and b separately, because this will be a will be then omega by omega n. So a will be equal to f naught by m omega n square minus omega square, and this will be a plus b, so 1 plus, so this is 2 and 1 plus omega by omega n, right? And the other term will be equal to, b will be equal to f naught divided by 2n omega n square minus omega square 1 minus omega by omega n. So it is not very difficult to find out that a and b will be of this particular form. So if you substitute that, then you will get the initial condition will be 0 and only the effect will be due to the force. Okay, let us take one example where the force is I took general, let us say now the force is Ft, this is sine omega t. What will happen in that case, sine omega t, you can check that the response F force, this will be equal to F naught divided by m omega n square minus omega square, and this will be sine omega nt, omega t minus sine omega, is this so? I mean omega t and no. Let us calculate. When sine omega t. Okay, let me calculate with the A and B part. So what will be the x force t? That will be equal to F naught divided by 2m omega n square minus omega square, then e to the power 1 plus omega by omega n e to the power j omega n t plus F naught divided by 2m omega n square minus omega square 1 minus omega by omega n to the power minus j omega n t plus F naught divided by m omega n square minus omega square to the power j omega t. So this will be the overall response. Okay. Now you see one thing that okay. So this will be the response. This is the zero force, zero initial condition response. It's a little complicated part. It's a little complicated because it will j omega n t, all this stuff will be appearing. Now you can get the value e to the power j omega n t from here. E to the power j omega n t. You can get that. So basic idea is that this is the part which actually has zero initial condition, and the other part will be a e to the power this thing, that is a to the power a cosine omega t minus omega n t minus phi. This will be the zero force response. So we can actually differentiate the total response into two parts. One is the zero force response and one is the zero initial condition response. In some physical in the system theory, this is also called the zero state response. You will learn about this later in your automatic control class, what is meant by state. But here we are considering the zero initial condition response. Okay. So let me now take a case where we study what is going to happen to this one. Let us take mx double dot plus kx equal to, let us say, f naught sine omega t. Sine omega t. Of course, the zero initial condition here, see, of one particular thing is that x steady state, we'll call steady state. This is actually what you are saying, that this will be the homogeneous, the response due to the homogeneous to the inhomogeneous part. That means the particular integral. So particular integral will be here in omega square minus omega n square minus omega square sine omega t. So this is the particular integral. Okay. Now, so this is the particular integral, and if we consider the block diagram as I have drawn earlier, that is 1 by m omega n square minus omega square. Okay. This, when you get the value fs, this will give you x steady state s. So the steady state response the force, the Laplace transform of the force, if you give it to the transfer function, that is, this is the system, transfer function of the system is 1 by m omega n square minus omega square. If the force is given, force is given, Fs is given to that system, then the response will be x s s s. So this is the zero initial condition, zero state response we have with a force Fs. Okay, so now if I denote this part, so let me call G Fs, actually Fs, I should not say Fs here, maybe it's better to write down in a square plus omega n square. So this is the response over here. Now if you have J S equal to J omega, that is, if you apply the harmonic excitation, then the steady state response XSS will be equal to 1 by m omega n square minus omega square e to the power j omega t. So this is the steady state response. Of course, it is not necessary that the zero initial condition will be satisfied here, but still we'll, for the time being, we'll consider this part a little bit in details and see what we get out of it. So you see now that I can write down this one xxx steady state, this divided by this one, this is equal to, let us say, 1 by m. That means if I write down g j omega e to the power j omega t. Okay, and I had force, so therefore if so this is the unit e to the power j omega t. If you have f naught e to the power j omega t, then naturally this will be f naught divided by m omega square minus omega square e to the power j omega t. So this thing, that is, this will be now, this was with initial e to the power j omega t, now it is with f naught e to the power j omega t. So this will be the response, steady state response. I will consider this as a steady state response. So this is not the zero initial condition response, but this we will call the steady state response. Now there are ways to represent the steady state response. First of all, G j omega is a complex number, complex function of omega. So what is that? We had the transfer function, that is 1 by m a square plus omega n square. Here in place of s, I have substituted j omega. So this is a complex number, complex function, and we have the real part of g j omega plus imaginary part, so j times imaginary part of g j omega. We can either plot, so this we can write down, or g j omega, I can get the amplitude part of it, that is g j omega, the magnitude, and e to the power I, which is phi omega, and phi omega, j phi omega, where phi omega is the phase part of this part, is the phase part. Don't confuse, don't get confused. Okay, let me say phi prime. So phi prime omega is the phase. Phase. It is by j omega, it is magnitude. Okay, so this is the phase part. Okay, to the power j phi omega. Also, we can show the okay, so these are the two ways we can represent the g j omega, because everything about the system is included in this function g j omega. The steady state response, everything about the steady state response is inside this g j omega. And now I want to show how the g j omega varies with omega. Physically, what I am doing, I have a system, and in this system I am applying an external force in the form of harmonic excitation. Okay, how is it possible to excite the system in this kind of with this particular type of excitation? Does anyone know how we can excite the system physically? How we can excite the system physically?
Sir, I just have a question, sir.
Yeah.
Sir, I am asking, sir, why are we never considering the, I would say, the homogeneous part, sir? Because there is no damping, sir.
There is
So
no damping.
the
Yes, I am considering the
homogeneous.
steady state response. There is no damping. This is not the total response. The total response will be what? This is the steady state response. It is only due to the forcing. As I said, this is only due to the force. Okay, not due to the initial condition. Even if so, the total response will be the response with initial condition plus the response only due to the force with zero initial condition. But here I am considering a separate thing. I am never telling that this will be the response at time t equal to infinity. This is the part of the response. The other part will come from the homogeneous part, which of course in most of the system will decay to zero, but in this system which we are considering, since there is no damping, it will never decay to zero, and there will be a contribution from the initial condition. Or even if it's not initial condition, from the because of the fact that even if the initial condition is zero, there will be some contribution. But anyway, what I am saying is that this is the response, which of course, although now here this is one thing which I want to say. Mathematically, this will not be the total response. But what will happen in physical scenario is that, of course, we agree and we understand that mathematically this is not the complete response. But physically, there will be always certain damping, small amount of damping will be present, which we know that it will be there unless we excite the system in vacuum, and then there is no absolute material damping, no friction at any point. Unless that happens, there will be always certain amount of damping, which is of course is very small to be modeled in our system, our equation of motion, because it's not appreciable, it's negligibly small, but still its effect will be shown at time t equal to infinity, t tends to infinity, because there the effect will accumulate, and this will be shown at time t equal to t tends to infinity. There you will see only this part practically. But of course, mathematically, there will be, if you want to study this problem mathematically, then there will be another response, another part, which of course will depend upon the initial condition. Okay. So that is why this is very important to study only this Gj omega. Okay, that means the, let us say, magnification or amplification. So I can say that this Gj omega is actually what is doing, this is the force, and this part is actually what is happening. So this is kind of an magnifying. Okay, magnifying is the magnification factor, kind of. Okay, so this is because of that the response is not exactly equal to force, but something else. So this is very important. In physical system we study because we know that practically this will be the response at the steady state. Whatever be the contribution of the initial condition, it will eventually die down, whether we have included in our model or not. But mathematically, of course, there will be other terms which I am ignoring for the time being. Is this clear to you?
Yes, sir.
Okay. So, so that is, we'll study separately. I mean, we'll just draw these two things separately. Now, let me first draw in this form. So I now have J omega equal to 1 by m omega n square minus omega square. Okay. So magnitude of J omega, this will be equal to 1 by m magnitude of that, and phase will be what? Pi prime omega, what will be that? You see, when omega is less than omega n, what happens? This becomes equal to 1. Well, this is a positive number. So phi will be 0 when omega is less than omega n. And what will happen when omega is greater than omega n? Then this will be a minus the negative number. Okay? That means it will be, what will be the phase change? Phase will be now pi when omega greater than omega n. What will happen when omega is exactly equal to omega n? Omega is exactly equal to omega n. This goes to infinity. And you see that this will be equal to pi by 2 when omega exactly equal to omega n. So this will be the phi prime omega. Right? So if you plot this one, then you'll see. So I'm plotting this with omega g j omega n. So at omega equal to 0, omega equal to 0, so this will be 1 by m omega n square, so this will be 1 by k. You see? At omega equal to 0, what will be? This is 1 by m omega n square, and this is nothing but 1 by k, because omega n square equal to k by m. Right, so it will start from 1 by k, and it will, so this is one extreme when omega tends to 0, so this will be constant. When omega tends to infinity, then what will happen? Omega tends to infinity. Omega tending to infinity.
0.
So, no, it's 0, but how does it vary? So what I am saying that what will be the asymptote to the curve? Asymptote. That means how the function will behave when omega is very large. You see that this function, say omega n will be, omega n is a finite number, so therefore this will be very small compared to that, and in that case this function will be going to omega n omega square, right? Because omega n is very small compared to omega in that case. So this will go to omega n by m omega square. And in between, when omega equal to omega n, this will go to, this becomes infinity. So the curve is something like this. It goes to infinity and it goes to 0, like this one is m1 by m omega square. So this is how the function g, the omega, this will go. And what will happen to the function phi prime? Phi prime, let me draw it. So phi prime, omega at omega equal to omega n, this will be pi by 2. Otherwise, this will be pi and 0. So up to this point, this will be pi, this will be 0. Here it will be this one, and at omega equal to omega n, this will be just pi by 2. So this will be the amplitude and the phase of g j omega. Sometimes it is useful to plot this one in the logarithmic scale, because there is a very large variation. You know that when the this is going, omega is very, so omega is very small, then when omega is capital omega, when omega is very large, so this becomes very small. But when omega is very near to omega n, this becomes very large. To accommodate this large difference in a single scale, sometimes we use logarithmic scale. Similarly, omega can be varied from 0 to megahertz. So therefore, again, a linear scale may not be sufficient here. So we can use sometimes logarithmic scale in this direction. Logarithmic scale, so doubly logarithmic scale can be used to plot the amplitude and the phase. Okay, phase. Of course, we do not plot actually phi prime in the logarithmic scale. Only we use the linear scale. But sometimes we use the logarithmic scale for g and omega. And when we plot this g versus omega in this logarithmic scale, we get a curve something like this. You can check that one, because so we'll get a response. um, in the logarithmic scale, if we get the, this one will have, and because in that scale with the log j omega and log omega. So if I plot that one, we'll get this kind of curve. Okay, where this slope is actually minus 20. This is 1 by 3. This is minus minus 20 dB per decade. So this is a curve which, of course, you'll know much later. I mean, later on in the other courses. But this kind of curve is normally seen when you plot logarithm of omega versus logarithm of gj omega. Dual degree students, can you recall what is this curve called? Can you tell? Can you tell me? This kind of curve
Bode plot.
is called the Bode plot. It's called the Bode plot. Okay. And of course, we have the phase information. That is, of course, there. Phase information will be 0 and pi by 2, pi and 0. This is omega. This will be log omega. Here, then pi prime. So this is the amplitude and the phase in the log scale. So this is technically it is called the Bode plot. Okay. Don't worry, for MTech students, you will definitely learn. Those of you who have had previous exposure to automatic control, they already know it. But those who are learning automatic control for the first time, they will definitely hear about this Bode plot later on in your automatic control course. So this is one thing. One interesting part is that here, when omega is going to be very small, that is omega tends to 0, this curve actually becomes flat, and when omega tends to infinity, this curve goes to, becomes asymptotically small. So this is going down at a very fast rate. Okay. But what happens here? What happens here? So that is interesting. That is here when omega is equal near in omega n, this actually amplitude is becoming very, very large. Okay. We'll in particular consider this portion when omega is exactly equal to omega n. But before going to that into that direction, let me also plot the other thing. That means I want to plot real part. So real part of gj omega and so if I plot, so let me, what I am doing is that here, so this is the S plane. S is the same complex number which actually appears in the Laplace transform. So if S is a complex number, so S is equal to alpha plus j omega. Okay. So that is the one. Now what I am doing here, I am considering S is equal to j omega only. And omega I can vary from minus infinity to plus infinity. S is j omega, omega can be, so omega is, this is the imaginary S which is equal to omega. Omega I can vary from minus infinity to infinity. So what I am doing, at different point we will have different omega. So this is nothing but omega. Omega I am changing. So that is how I am plotting this curve. Say in the Bode plot, omega was in one scale, the x-axis, and I plotted g and phi prime separately. But now I want to plot real part and imaginary part on the same curve, but now on the same graph, but now I have to change omega and I have to show the omega as a parameter on the curve. So that means what I am doing, I'm changing my omega value, and correspondingly, so what I am doing here, real part of g and imaginary part of g. So here what I am doing, I am changing my omega. So let us say I am choosing this particular as the omega. I find out the corresponding point, real part of g and imagine real part of G and imaginary part of G, and so this actually the corresponding point here, right? Similarly, when I take this value, I get another point, this one. So from 1 it goes 1 prime, 2, 2 prime, maybe 3, 3 prime, and so on. So when I vary continuously with omega, I will get a curve in the imaginary plane here. So real G and imaginary G, I can plot a curve over there. So if you try that, then what you get is this thing. Okay. So minus infinity to infinity. This is this omega. Omega is from minus infinity to infinity, and I am plotting here real G omega G and imaginary G. So when it is where G is actually 1 by m omega on omega n square minus omega square. So when it is minus infinity, what is going to happen? What is going to happen? This will go to, so when we start to minus infinity, the absolute value will be 0, right? Because 1 by m omega n square minus omega square, right? So where should we place this point when omega tends to infinity? This will be a real number and this will be negative, right? Real number and negative. So it will start here. 0. So this will be 0 from this side. So this will come to 0 because here. So this comes to 0 from this side. When omega is 0. So let me consider first. Omega is 0. Then it will be omega 1 by m omega n square. So it will start from here. As omega increases, then what will happen? From 0, it is increasing. It goes to omega n. So omega n and minus omega n, these two are the two numbers which we have to be very careful of. When it approaches 0, it goes to infinity, right? It is going in this direction. It's going 0. So from here it is going this side. And then what will happen when it goes? So when it reaches omega n. So what I am plotting is omega is starting from 0. You see that when omega equal to 0, 1 by m omega n square minus omega square, this starts here. When I increase the value omega gradually, you see that this value, when I am increasing this value, so therefore this value is decreasing, so this increases. The ratio is increasing, so it is going in this direction. Now, I cannot, so one thing is that this point is actually a singular point, so that means because it blows up at omega equal to omega n. So what I have to do, I have to just take a small detour around this point and then proceed. So I cannot plot exactly at omega equal to omega n. So what is going to happen here is that this part is actually, it goes to infinity when omega goes to omega n, and at omega n actually it abruptly changes its sign. It comes here, it becomes, so from positive infinity just flips over, so it becomes a negative infinity, and then gradually it goes to 0 from this side. Okay, so this is what is going to happen here. Now exactly the same thing will happen if you consider the other part. That means if you proceed from this direction, then proceed from this part. So you'll see that. So I plotted only up to 0 to infinity. You can plot also minus infinity to infinity, and then you'll get similar kind of part. So just here it goes to 0, and then here, and so this will be a kind of a curve which is a very big circle. When this goes, the radius of the circle almost goes to infinity. But this interesting part is actually lying here. So it starts from 1 by m omega n square and reaches, it goes to infinity. So this is one way of also showing the similar kind of response. My dear dual degree students, can you tell me that what I am drawing here? What is being drawn? What is this that I am drawing? Come on, you learned it in your systems control class. This is called the Nyquist plot. Bode plot and Nyquist plots are two very important useful tools in control engineering. That means in the system theory, not control engineering exactly, but in the system theory. And our system is nothing but a physical system, so we can show everything with the help of these tools, like the Bode plot and the Nyquist plot. But one thing is very clear here, that is at omega equal to omega n, G actually goes to infinity. G goes to infinity, Now what happens then? What kind of response do we get that time? So that is quite interesting and we'll have to study. Before that, let us consider another case, mx double dot plus kx equal to f naught, let us say sine omega t. And we have so xt will be equal to a cosine omega nt minus phi plus f naught divided by k minus, so m omega n square minus omega square sine omega t. So this is what we have. And if we consider let us say zero initial condition, let me consider the case with the zero initial condition. Let us say x0 equal to 0 and x dot 0 equal to 0. So what we get from here is that x0 will be equal to a cosine a cosine phi, and that is equal to 0. That means phi equal to pi by 2. Phi equal to pi by 2, and x dot 0 equal to 0. That means minus a omega n sine phi. This equal to this plus f naught omega divided by m omega n square minus omega square sine cosine phi, and that is equal to 0. That is equal to 1. So now we get phi equal to that, and a equal to, what will be a sine phi? A sine phi is equal to a is equal to what becomes this is a sine phi. So this is pi by 2, and then this becomes this is a equal to f naught omega by omega n divided by m omega n square minus omega square. So then the response with the zero initial condition. So zero initial condition, the response will be equal to xt f naught. So what will happen to that? This will be f naught sine omega t, and this is a equal to this part. So therefore f naught divided by m omega n square minus omega square, and this part will be equal to omega n So this you can say that this will be 1 by omega n, omega by omega n, 1 by omega n sine sine omega n t plus sine omega t. I made a mistake possibly here. It will be sine. I made a mistake says because this is cosine omega n t minus pi, and this will be cosine omega n t minus pi by 2. Okay, so cosine n t minus pi by 2, that will be sine omega n t, and let us check this part. So what is going to happen to this xt? X dot t equal to 0. X dot t, what is this? Omega n, omega minus omega n cosine omega t. So at t it is satisfying t equal to 0. X0 equal to here sine 0, and x dot 0 will be equal to what? Omega n 1 minus omega by omega n and plus omega. No mistake. So this is what we are having. Anyway, let me do this again. So this part is not exactly correct. So what will happen is a cosine phi, or maybe I'll consider a sine omega n t plus b cosine omega n t plus f naught divided by m omega square minus omega n square minus omega square sine omega t. So this is xt. So x0 equal to b plus f naught divided by m omega n square minus omega square into 0. So therefore this is equal to 0, b equal to 0, b equal to 0, and a equal to, so x dot 0, this will be equal to a omega n plus f naught divided by m omega n square minus omega square times omega, and this is equal to 0. So a will be equal to minus f naught by m omega n square minus omega square times omega by omega n. So that is what we are having. So therefore this will be equal to this one. So 1 minus, so that will be sine omega t minus 1 over omega by omega n sine omega n t. So that will be the response with 0 state or 0 initial condition. So this is the response with 0 initial condition. Fine. Now to see one thing is that I want to study that what happens when omega equal to omega n. So what happens to this particular response when omega becomes equal to omega n? Can anyone tell what happens when equal to omega n in the response? From the diagram, we have seen that this goes to infinity, right? The amplitude goes to infinity, but how does it approach infinity? So that is the question. It goes to infinity, but how? Can anyone tell? Exponentially. Okay, let us see what happens. Okay, now if you plot, now what will happen? So this is the from the 0 initial condition. Okay, so with t, if I plot xt, again I said that this is with the 0 initial condition. The other part, the initial condition, the effect of the non-zero initial condition will be taken separately. So this is the 0 initial condition case. Now xt, what we get when we plot xt here? What happens to that? You see, in general, these two will be actually a kind of aperiodic function. Why aperiodic function? Because there are two frequencies omega and omega n. When will this function be periodic? So it means that in general, as you are saying, someone of you were saying that it is undamped system. So at time t tends to infinity, if you do not consider damping even physically, then what kind of response do you get? You will get kind of an aperiodic response. This is very, counterintuitive. That is, we have a vibrating system, we are exciting with the harmonic excitation. Still, the response is becoming a kind of aperiodic response. There is no periodicity. Okay. It's very counterintuitive, but it happens because there are two signals which is having two different frequencies. Can anyone tell when will the signal become periodic? Is it in general aperiodic? The signal is in general aperiodic. Now, when periodic? When will it be periodic?
Sir, when omega equal to omega n.
When omega equal to omega n. No. When omega by omega n is actually a rational number. That means it can be expressed as a p by q. So either omega is, any omega by omega n is a rational number. You can say that means omega p, omega q equal to omega n p. In that case, there will be after a long time, it will actually becomes they repeat each other. And I suggest that you find out what is the time period for this signal, signal to be periodic. Okay. What is the time period of this periodic signal when omega by omega n is p by q? Please take this as kind of a small exercise and think over this. So what we get is that when omega is equal to omega n is of course p by q form, but it will not be periodic because at omega equal to omega n something else will happen. So at omega, let us say 2 omega n, it will be periodic, 3 omega n or half omega n, this will be periodic, and so on. So periodicity condition when you have two signals, two harmonic signals, are periodic when the frequencies are commensurate. That means their ratios will be a rational number. So there is a rational multiple of R. Now, what will happen when omega goes to omega n? What happens when omega goes to omega n? Let me see, that is, suppose when omega is very small, omega n plus, let us say, delta omega. Let us say very near to omega n. Omega is very near to omega n. Then what kind of response do you expect? Sine omega t minus omega by omega n sine omega n t. This is approximately sine omega t minus omega by omega n when delta omega is very small, so therefore this will be omega n plus delta divided by delta omega divided by omega n and sine omega n t. Okay. So this will be sine omega t minus sine omega n t, okay, minus delta omega by omega n sine omega n t, right, when it goes to small t. So this part, then this becomes equal to 2 sine omega plus omega n by 2 t and sine times cosine omega minus omega n by 2 t and minus delta by omega n sine omega n t. That is what we have. Now, what kind of response this will be? So it will have, so this omega plus omega n by 2 is approximately equal to omega n. or omega, but this part is actually delta omega by 2. So this response will be something like this. So this part will give you the response something the response will be something like this. Over and above, there will be a small contribution delta omega by omega n. So if delta omega is going to be very small, tending to 0, so this will be negligible, but you'll get a response something like this. So what kind of response this is called? What kinds of response we call this one?
Beating response.
This is the beating. So when omega approaches omega n, we get a beating response. Okay, there are two closely separated harmonic signals present in the response. So therefore, we'll get a beat. Now, interesting thing is that what happens when omega is exactly equal to omega n? Omega is exactly equal to omega n. One thing is that said that the response, what is the time period? 2 pi by, so time period, so there will be two signals. One is this signal, which is actually a high frequency signal. Now I hope by looking at the signal, looking at the graph, you can actually understand what is the, what you have a feeling of the frequency of the signal, of the signal, right? So there are two periodic things, like this is periodically varying, like this, and inside this envelope, so there is another periodic variation. Which one will have a higher frequency?
Inner one.
Inner one will have higher frequency. This you have to be very careful, and this idea you should develop with by looking at the signal. What is the nature of the frequency? Whether this is high frequency or low frequency, and so on. So this is definitely a high frequency signal. And what is the high frequency signal here? This is omega by omega plus omega n by 2, which is approximately omega by omega n. This frequency is approximately omega frequency, right? Omega plus omega n by 2 equal to omega plus delta 2 omega plus this thing omega minus delta omega. So delta omega is very small, so this approximately equal to omega. The other part here, this one is the envelope. That means the amplitude is actually modulating with a frequency. This is with a frequency. What is this frequency? This will be delta omega by 2, right? Because this is delta omega by 2. So with this small frequency, it is actually modulating. Now what will happen when omega is equal to omega n exactly? Then what we expect? We expect that this will be like that, but this modulation frequency will be 0. That means the time period of this modulation will go to infinity. That means that it will never come back just like a modulated signal. So what we'll expect that it will go to, it is always going to increase. It will never come back. Okay, that is what the expectation is. I hope you are understanding me. So when delta omega becomes 0, then this time period goes to infinity. That means there is no coming back here. So this envelope will never revert its path. It will never come back. So it will always actually diverge. So this is what we have an expectation of this kind of response, that there will be kind of beating with a bit frequency 0. That means it will never beat, but it will always go on increasing. But let us see what is the exact nature of this curve. So now what we are doing, I will put what happens when omega is actually equal to omega n. When omega is equal to omega n, exact value we cannot say, but let us see when omega tends to omega n. Omega is tending to omega n. You see now xt, so what we will find out? We will find out limit omega tends to omega n xt. That is the response when omega n, then omega tends to omega t and omega. So this will be f naught by m, and limit omega tends to omega n, right? So this will be sine omega omega n sine omega t minus omega sine omega nt divided by omega n square by omega square, right? I'll have to find out this part, omega tends to omega n. So this is how you'll have to find out, okay? Right? So what will be the limit? How do you get the limit of this? You
L of
see
it
here,
all.
we take the limit, but numerator and denominator both are tending to 0 when omega is exactly equal to omega n. When omega n tends to omega, then numerator and denominator, both of them are becoming 0. So then the way to take this limit is to use the L'Hospital's rule, or then this is actually I'll have to differentiate with respect to omega and put omega n. That means this will be equal to differentiate with respect to omega here, so therefore omega n. So this will be omega n, omega, I'll differentiate with respect to this, so therefore t cosine omega nt. So I'll first differentiate, let me first differentiate. Omega t with respect, this is minus sine omega nt, this divided by minus omega n into 2 omega, right? And then put omega, then limit omega tends to omega n. So if you put omega n, then this is omega n, and so on, then you get the response like this. So when limit tends to this omega tends to infinity, you get the response like f naught divided by m 1 omega, by 2 m, this becomes 2 m omega n square, and this becomes equal to sine omega nt minus t omega nt times cosine omega nt. So this will be the response when omega tends to omega n. Omega tends to omega n, this will be the response. Okay. And what kind of response it will be? See, there will be a bounding term, this is sine omega nt, but this term, t omega cosine omega t, so therefore there is this one part is actually a kind of harmonic. The other part is also harmonic, but now its envelope is actually becoming minus, so therefore the envelope is like this. So if you consider only these terms, so therefore initially there will be some disturbance because of this term, but eventually this actually goes to this envelope goes linearly with time. Okay, so this part of the response omega nt. So there is a signal, harmonic signal cosine with omega n frequency, but this envelope is actually going to increase with time in a linear fashion. So I can say that is my earlier observation is initially it was correct because the because in the beating we had this kind of phenomena. Now what is happening when omega tends to omega n, then this beating frequency becomes very small, so therefore the time period of beating very large. When omega is exactly equal to omega n, then the beating stops, and actually what will happen? This becomes actually, so this part is never coming out, so therefore it will go to infinity this way. So it will go to infinity. So that is our earlier intuition, our earlier observation was in accordance with the correct result. Is this clear to you? Now someone was saying that it will increase exponentially, but it is very, very important to know that this is definitely not going to increase exponentially. This is going to increase linearly. Exponential increase is something different, which is which leads to catastrophic failure because exponential function goes up very fast. But the resonance gradually builds up. It does not immediately break, but finally it will definitely break or modify the system. because the amplitude goes to very high value with time, but it increases, the response increases linearly. It does not, I mean the envelope increases linearly, it does not increase exponentially. Is this clear to you? This mathematics was clear to you? Please tell me.
Yes, sir.
Okay. So in resonance, we have, so this condition, that is when omega is exactly equal to omega n, we call resonance. Okay. And then in the resonance, what happens? The amplitude builds up. It goes to infinity, but the amplitude increases linearly and goes to infinity. Is this clear? So this is phenomena is called resonance. Now, at this point, let me consider the this resonance part. Here, just a little bit more about this. So I have this one, mx, yes, kx plus equal to this. If not, let's say sine omega t. Okay, sine omega t. And then then I want to find out, so the response, the steady state response part, this will be equal to f naught divided by a minus m omega square, a minus m omega square, and sine omega t. So this is the steady state response. Okay? Okay. Now, and of course, there will be a cosine omega nt minus phi. Omega nt minus phi. Now the velocity of the signal, this is velocity. Velocity of the signal will be equal to f naught divided by a minus, derivative of the signal, it's not the velocity of the signal, cosine omega t minus a omega n sine omega n t minus phi. Now, what is the work done, or what is the power? So this is the response, right? So what is the power? Power will be force times the displacement, velocity. So this is the power. And what is this force? This is f naught sine omega t, and x dot is like that, certain part, that is f naught divided by a minus m omega square times omega cosine omega t minus a omega n sine omega n t minus phi. This is the part. Fine. Okay. Now, if I want to calculate the energy change or the work done, okay, in a cycle, so work done in a cycle. So this is the integration of this power over dt, and 0 to, let us say, 2 pi by omega. That is, over the cycle, I want to find out what is the net power, net energy, or work done by the force. Okay, so what is the net work done? And then you see that the first term, that means equal, that means this term, that is f naught sine omega t by k minus m omega square f square, and then the omega term is there. And if you integrate 0 to 2 pi by omega n omega t, of course, the sine and cosine t, and minus a omega n sine omega n t minus phi times sine t at 0 to 2 pi by omega t. Okay. So I have just substituted this and integrating with respect to time over 0 to 2 pi by omega. That's over one time period of excitation. So what is going to happen to this? What is going to happen to this this integral sine omega t cosine omega t dt over 0 to 2 pi by omega? What is going to happen to this? Yes? This goes to 0. I hope all of you. And F naught. So F naught is there. F naught is there. F naught I forgot. F naught sine omega t this time. A times F naught omega n. Now what is going to happen to this integral? What is going to happen to this integral? Let me consider. So this W equal to minus A omega n F naught and 0 to 2 pi by omega, this is sine omega t, and this one will be equal to sine omega n t cos phi minus cos omega n t sine phi. This is t, right? Fine. Okay. Sine phi, all right. So that is what we have here. Now, what will happen to this integral? What will happen to this integral? When omega is not equal to omega n, what will happen to this integral? Can anyone tell? Now this is something which you can visualize and say. What happens to this integral when omega is equal to or is not equal to omega n? Now you will see that this signal is actually when omega is not equal to omega n, there is a high probability that sometimes this part omega, sometimes this will be positive and negative, and you can visualize and say that when omega is not equal to omega n, then there may be very small contribution from this integral. Okay, but when omega, that is because this term, these are with different frequencies. So actually, in a one particular thing, so at one time period, maybe it will be so oscillatory that the overall integral may vanish. So this is more or less the expectation. Real mathematical thing you can find out and derive it, but mostly, and if you want to take maybe this is over one time period, but if you want to take let us say n time period where n tends to infinity, so over a large time interval, so I want to find out the net energy change in n time interval and divided by the n, then I can get the average change in the energy. So average work done. So an average work done will be this the net work done divided by n when n tends to infinity. Okay, so this you can say that when you calculate this integral over a large interval of time, then this will be so oscillatory that it will actually become almost equal to 0. So there will be no contribution when omega is not equal to omega n. But what will happen when omega equal to omega n? Exactly equal to omega n. Then of course this will be contributing, right? Sine square omega n. So it will be sine square omega n, sine omega n cosine omega n. So this part will not contribute, but when this is there, so I'll get minus a omega n f naught, and this will be cosine phi. So therefore, cosine phi by 2 times 2 pi by omega equal to omega n. So I'll get let's say minus a f naught cosine phi times phi. So this will be the work done when phi is the contribution from the initial condition. So now you see when there is no resonance, so W tends to 0. When there is no resonance, actually it does the when there is no resonance, the work done by the force is equal to 0, almost equal to, and very negligible. Because what will happen? Over a part of the cycle, the energy will be drawn from the excitation source, and in the other part of the cycle, it will be given back. So over one time period, there won't be any net transfer of energy from the source. Okay. But what is going to happen when we have the resonance? Only during resonance there will be this is the average power. So over a cycle, like this. So therefore, over a cycle. So this is actually A and phi. So these are actually depends upon initial condition. So over a cycle, there is a constant amount of energy which is being drawn from the source. Okay. So the source is actually supplying a constant amount of energy per cycle. So as the number of cycle increases, so therefore the total energy expended by the source also goes to very large value. This is becoming clear to you, what I am saying? When there is no resonance, that is omega is not equal to omega n, source does not do any work in the net over a time interval. Okay, or over a period, it does not do any work. Is this clear? But when there is the resonance, then the source actually does work. The energy gets converted into the vibrational energy from the source. So the energy comes in. So it is very contrary to our intuition that although the system is vibrating, but there is no net work done by the force over time interval as long as there is no resonance. But what happens during resonance? During resonance, actually a small amount of energy will pass from the source to the system. And as the cycle, the number of cycle is increasing, so this is a constant amount per cycle. So as the cycle, the number of cycle is increasing, so at each cycle, some amount of energy is drawn from the source. So what is going to happen during resonance? During resonance, the system is actually will get energy more and more, and small amount of energy every time it will get over time. Okay. So per cycle it will get some amount of energy, let us say W. Next cycle it will get 2W. So therefore, total energy will be 2W, 3W, 4W, and 5W, and so on. So you see the energy is increasing at a linear rate. Okay. So we expect that the amplitude of the vibration will also increase as the linear rate, because the energy is being increased as a kind of linearly increasing. So and of course, F naught is there, so amplitude will increase linearly. Now, here, that is very important thing. That is, during resonance only, it draws a large amount of power from the source. And that is expected because the system was a finite system, is a linear system, but it is getting excited to a large extent. Then wherefore it is getting the power. It is definitely drawing the power from the source. But this does not happen during resonance. In the resonance, no power is drawn from the source. Only during resonance, power is drawn from the source. Okay. Now, one thing you may say that, okay, one part is that suppose we have a source and the system is getting excited to resonance. So suppose the resonance is taking place. Resonance is taking place. So one way, let me say that maybe I have a system. And there is a motor. And this motor is, let us say, rotating with speed omega. Okay. And this system can only now, this is the mass and stiffness. This is a big mass and a small mass, like you see. And at a distance, so this can be when the eccentric mass which is being rotated by the motor. Okay. can you find out the response, the steady state response of the system? First find out the equation of motion, and from the equation you can find out the steady state response when the motor is rotating at uniform speed omega. Let us say suppose the motor speed we can change with the help of a resistor. We can change the motor speed. So there are techniques for controlling the motor speed. Suppose the motor is rotating at the speed omega and we want to know what will be the response. So this is one way to excite the system. So what will be the what will be the equation of motion? Can anyone tell me? What is the equation of motion of this? Assume that the mass of the motor and this mass together actually weighs capital M. So there is a M is the net mass of the motor together with the block. So what will happen?
Capital MX double log.
From the equilibrium position, so equilibrium position will be a little bit low because of the weight. It will go down a little bit. So if we measure x from the equilibrium position, that means this is always our case. That is, we are measuring the x from equilibrium position and linearizing. Okay. So linearized equation of motion will be now m
X double dot
x double dot plus x equal to
me small me omega square sin
omega square.
sin omega t sir.
If you start measuring from this at t equal to 0, suppose it was there, so sin omega t. Carefully check whether this will be m or small m. Please check this. Only capital M or a small contribution of this small m will be there. Of course, this is negligible. Approximately equal to m. It's very negligible mass compared to big mass, but in the correct equation of motion, you should be able to get capital M plus small m. Right? Yes or no? Write the total kinetic energy. Total kinetic energy will be what? Half m v square plus half m. What is the mass of this thing? This will be v plus this is in this direction. The v will be only v plus e sin omega or c sin theta or sin omega t. Isn't it? Okay. So you will get that this is becoming m plus m. This term will come v square plus m v e sin omega t, and this plus half in v square sin square omega t. Okay.
Sir, it should be E sin omega t dot.
Sin omega t dot.
E omega sin omega.
Yeah, E omega cos omega t.
Right, e omega. So the omega term will be there, right?
So it should be cos, no?
By cos.
Means the derivative of E sin omega t. That is velocity, right?
Oh, you are right. This is cosine. Yeah. Okay. Right. So you see that this term is going to appear and that will compute here. This term, you can say that this term ddt of this term will give you del t, del v will give you this part. Time derivative of this will give you sine omega t times omega, so me omega square term will be there, and kx will come from the potential energy. This is not going to contribute to anything. Okay, fine. So this is the correct equation of motion. Of course, as I said, I mean, as we are saying here, that this is approximately equal to capital N, but exactly this will be capital N plus small n. The effect of this mass will be also felt on this body. Okay, now if this is so, supposing now as we are saying, maybe here x double dot approximately, neglecting the mass of that part. So here, if I get the response, that means x dot, x will be equal to the steady state part. Steady state, again, it is not the non-zero, I mean the zero initial condition solution, but it is the solution only due to the right hand side. Okay, so that means the particular integral. So m e omega square divided by k minus m omega square and sine t. Okay, so now what will happen to this? Now if I want to plot, so therefore this you can see that this will be, if I write down this g part, so g j omega, again this will be equal to minus m e s square divided by k minus k plus m s square, okay, capital M s square. So that's it. So either you plot that, or let us plot directly. So you can plot the Bode plot or the Nyquist plot, all these things. You may try out this one, but let me plot similar directly the one, that means that this part, that means only the modulus of this part, omega, and let us say xss. If I write down this as xss, that means this part as xss only, then you see at omega equal to 0, this will be 0. And at omega tends to infinity, what will be that? Omega tends to infinity, this will be, what will be this? Omega tends to infinity. Omega tends to infinity, it will be equal to me by e. So very small there, and at omega equal to omega n like this. So therefore, the response will be something like this. Okay. That. So therefore, m by m. So amount, very small amount of residual response, will be residual displacement will be there at a very high frequency. So this is how the system will behave. Now one thing is that here at resonance, I hope all of you should be able to draw this curve. This response, what we are drawing, this is known as the frequency response function, frequency response of amplitude. So amplitude frequency response or frequency response of the amplitude. Similarly, we can draw the frequency response of the phase difference. Okay, so phase frequency response or the frequency response of the phase, both the terminologies are used. So this is the frequency response of the amplitude. In many of the vivas, we ask the students to draw the response and the frequency response. They get that, but when we ask them to find out the time response, then they draw the same curve. So please make sure you understand the difference between the time response and the frequency response. Time response is actually drawn with time as the x-axis. Frequency response is with the omega as the x-axis, and there we show only the steady state part. That means only the the particular integral of the solution. Okay, homogeneous response, that is the other part of the response we do not show here. We consider only the particular integral. Okay, the amplitude of
Sir, we are considering only absolute value of the amplitude, right, sir?
We are considering only the absolute value of the amplitude. Exactly. So that is another thing, XXS. So I got this modulus of this. The other curve actually obtained is a phase one. So in the phase, again, you'll get this is 0 and this goes to pi, and that resonance will be pi. So this is a phase one. The amplitude, so the frequency response of the phase, okay, and the frequency response of the amplitude. The frequency graph of the amplitude and the phase are drawn here. Now, what happens when the resonance takes place? Then what happens? See, how do I do this experiment? Suppose I want to find out this curve through experiment. Then what do you do? What do you do? We take the motor. Again, remember the system which we are dealing with. We have a motor. As the motor is there, M, E, and this is rotating omega. So there is a control device. So the controller, and I give the voltage to the armature of the to the motor, and then by changing the voltage, I can change the speed. That is clear. So I take with a very small speed and increase it. So a very small speed, I increase, I find out the steady state response. Of course, here there will be some damping, because of which the contribution of the initial conditions, these things will not be there. Only the steady state part you will get in a physical system, real physical system. So we get the measurement and get the response. Okay. Now, interesting thing, how do we measure the response of the system? What is the techniques of measuring? How do we measure the response? I said that you measure the response, but how do we measure this response? Can anyone tell me? How the response is measured?
Camera.
Camera. Well, camera is not a good tool, because then the response, the measurement will be very erroneous. Okay, there will be a lot of error, because the light signal, they will be contaminated with noise, and there will be very large, small error will be amplified if you have the camera system. Camera may be one thing, you can observe it and see it, but it's not a very good tool. So, yes? Yes?
Sir, accelerometer.
Okay. There are devices, so accelerometer. Okay, accelerometer. Any other meter? So in accelerometer, what we do? We put the accelerometer on top of it or attached to the thing, and we get a signal which is proportional to its acceleration, or then it can be integrated to get the result proportional to the displacement. Fine, that is one thing. But accelerometer has certain disadvantage. I'll talk about it later on. There may be other ways to get the measurement. For example, we can have a capacitive sensor. That means we can find out the distance between the moving plate and the fixed plate by measuring the capacitance. So there will be electrical circuit where we can measure the capacitance. So by measuring the capacitance, we know how much distance is actually traversed, and from that we know the displacement. Okay, so this is one. Accelerometers are actually contact type sensors. So this is a contact. Yeah, the physical contact is there. That may not be good always. I'll talk about it later on. So there are other signal non-contacting type sensors. Non-contact. Okay. Like the laser vibrometer or laser. I put a laser, and there is a Doppler effect in the laser, because of which the frequency gets modulated, and then we can find out the change in the frequency, and from that we can find out what is the velocity. We can measure the velocity, we can measure the acceleration, we can measure the displacement. So there are many ways of measuring that. So what I am saying is that suppose we have the system, I excite, I'm rotating the motor, and I'm getting the response. Okay, response, that is, I am getting the measurement with the help of an accelerometer or any other non-conducting type sensors. Then what do we do with this sensor? This sensor signal, this electrical signal, they have to be fed into some device to find out the amplitude and the phase, right? So what are those devices? Can you name? Do you know? These are called the spectrum analyzer or FFT analyzer. So there are devices to get the amplitude and the phase of the response known as FFT analyzer. Earlier days, people used to use the cathode ray tube or cathode ray oscilloscope to see the signal, but nowadays normally use the digital technique. So this is the fast Fourier transformation. FFT, fast Fourier transform. This is actually a kind of discrete Fourier transformation, faster version of the Fourier transformation algorithm. So you know the Fourier transformation, but this is hard to implement in computer. And in 1960s, a kind of new algorithm has been developed, which is order of a few orders faster than the conventional integration method. So this is known as a fast Fourier transformation techniques. It's actually a faster version of the digital Fourier transform or discrete Fourier transformation, that is the DFT. So faster version of the DFT, this is the fast Fourier transformation FFT. So let us assume that we have the FFT analyzer and we know the amplitude and the phase. So what we get the amplitude. So at one particular omega, I excite, that means I rotate the motor at that speed, and then the excitation frequency is there. I measure the response. Okay, I measure the response. What will happen when we approach to omega n? So that is the question, right? When I got a curve, like very nice diagram like this, mathematical. But when I want to verify it, I have a problem, because the motor, as soon as I approach this omega n, what we find is that the motor power, as it goes to omega n, the motor is actually getting depleted in power. That means more and more of the motor power is drawn. And battery, so because this is driven by a battery finally, so motor is actually driven by a battery. There may be resistance, internal resistance, and so on. So the motor is driven by a battery, okay, which has a voltage. So therefore, it cannot give infinite power, right? And well, up to this point, it can go, because we see that it is not drawing any power. As I said that if there is no damping, of course, always will be some damping, and because of that, the power will be needed. But assuming that there is no damping, perfectly undamped system, so in that case, up to this point, there won't be any power drawn. So therefore, it will work comfortably. But when omega is equal to omega n is reached, what will happen? It will require infinite power from a finite source. Okay, so that it will not be able to deliver so that much of power, because when resonance takes place, that is omega is exactly equal to omega n, then at every cycle we need a finite amount of power. That is, I say, f naught cosine phi and phi. Like that. So at every step, at every cycle we need. So therefore, after a long cycle, we need a huge amount of power, huge amount of energy, which the battery cannot deliver. Okay. So what will happen? The motor will stall. So it will, even if we change the voltage, it is not going to move to the other region. So that is interesting phenomena we see, and this phenomena was observed by one physicist called Arnold Sommerfeld, and this actually called Sommerfeld effect. When we study damping, I will talk much about the Sommerfeld effect. But here the Sommerfeld effect is that, supposing, so what I am saying is that, suppose I have a voltage source here. So what I am doing, I am increasing this voltage from 0, and I am measuring the response. Okay, so this is what I expect. So at a particular voltage change, omega will be changing, right? So if you increase the voltage, it is going to change, right? Omega. And suppose it has reached 2, so this is omega versus voltage I am considering. Omega means that the rotational speed of this. when it reaches to omega n, it can go very well up to that. When we try to increase V naught further, then what happens? This cannot increase the voltage, because whatever voltage you give, this amount of power is actually consumed by the vibrating system. So here in this particular situation, it is not going to increase. Whatever change in the voltage you give, it gets stuck here. So this cannot go this far. Okay, you can of course come back from this side. Again, the same thing happens up to this point. Here we can get very high voltage, so therefore from very high voltage you can come and directly come here. But at this point, so while coming down, so while actually increasing voltage, you'll get this curve. It never goes to very high speed because it gets stuck there, because the high amount of requirement of high amount of energy. When it is coming down, that means from very high voltage, suppose you start from this side with a high frequency, then it goes there, but after that it gets stuck. So whatever value you change, it gets stuck to omega n. Okay, so it's increasing side, so this will be slow, and the posting down side, this will actually the omega is not going to change further. As is hits the peak, that means that hits the resonance. So this kind of effect is known as the Sommerfeld effect. I'll talk about it later on when we study damping, because it will be more useful there. But one thing you see that whatever theoretical results we are predicting, that may not be actually realized, that may not be seen in experiment. Okay, so one thing is that this is the modeling error, because what will happen? We assume the source of excitation, that is F naught. So we assume that there was some excitation which was giving the source F naught sine omega t, the force, irrespective of what is the motion. But now we see that this may not be possible under certain condition. Okay, we consider the source to be ideal source. That means it has infinite energy, but practical machines will not be able to deliver infinite energy, and then in modeling the resonance, we'll have to actually consider the dynamics of the source as well. We disregarded the dynamics of the source, says that okay, it is some energy source which is capable of giving the power or excitation, irrespective of what is the power requirement. But real sources cannot give that much power, and because of that, we see appreciable deviation from our expected results. Another thing which is actually modeling, that is we consider, well, this I wrote, I drew it and you accepted that, but then we always forgot that our model was a linear model. Okay, our model was a linear model because we disregarded the nonlinear terms. Why? On which ground? We assume that the response is small, so therefore all the higher order quantity, x square, x cube and other terms, these we disregarded in our equation of motion. Okay, this is true as long as x is small, then x square will be further smaller, x cube will be even smaller and so on. But when this becomes large, then we cannot neglect that part, right? So this is what is our prediction from the linear analysis, but we must remember that we are working with the linear system, and for the linear system, this may not be the correct one, because we our assumption was that the response is small, but here we are predicting a result where the response is very large. So there is an inconsistency in our modeling, isn't it? Did you understand that why? Where are the difficulties? I mean, we assume many things in our equations, okay, but we forget later on that is what we assume. And then, okay, we keep on, we present the result, we'll say that this will happen, but this never happens, because we had a basic mistake in our first step when we assume certain things, and here this assumption is violated. Is this clear to you? Is this clear?
Yes, sir.
Yes, sir. Okay.
Yes, sir.
So now you should
Sir,
understand that, yeah.
So like when we decrease the voltage from a higher value in the first
Yes.
graph, so the rotational velocity does not go beyond, it does not decrease below omega n, right?
Does not decrease below omega n, right? it gets stuck there. Okay, it gets stuck there. Well, whatever this energy, it cannot. You try to decrease the value, but it goes in increasing. I'll talk about it. It is not that you are right, maybe. So there's a kind of jump. Without damping, it is very difficult to see. So here you mean to say that, okay, when it is coming down, it gets stuck there. If you want to change that one, then suddenly there is, I should say, so when it is increasing this side, ideally speaking, yes, I think I should reconsider about my statement. It ideally should not go, get stuck there. But what will happen that there will be a large jump because suddenly it had huge energy stored here, right, at this point. And if you decrease, then that amount of energy will be suddenly released. So there will be a very uncontrollable and very kind of discontinuous phenomena at this point. What will happen that here, while what is more important is that while going up, it will not be able to cross this limit. So it will get stuck there. So the speed will be getting stuck. Okay. But while coming down, moving down from a very high speed, this will go up to this point. At this point, of course, it will stop working. But if you release that, actually beyond this point, it will not be able to do anything. Beyond this point, so you can decrease the voltage. You can decrease the voltage, but still, I believe that the speed will remain. Decrease the voltage. Up to this point, this part is clear to you, right? So if you increase the voltage, it does not matter. Omega gets stuck. While decreasing the voltage to 0, so you mean according to this curve, so there will be a huge requirement. Omega. We'll have to think over this. This is not exactly, so this I had drawn it, but maybe some physical inconsistency. But well, if you decrease the voltage, then the power is less. Suddenly, a huge amount. So in this curve, actually, what is going to happen that here it will get stuck. So omega will get stuck here, and it will never able to cross it. So that is what is going to happen. But even if the voltage, if you decrease, so so actually, what I meant is that it will never be able to cross from this side or that side. Okay, it will never be crossed. It will never be able to cross this region.
So then, like, those two curves will not be intersecting, right? At that point.
Here.
The decreasing curve and increasing curve.
Decreasing and increasing. So that no, what I'm saying. Yeah. So you're right. So here up to this point here. But omega voltage, and so actually the ideal curve is like if you increase the voltage, the speed will increase. So this is the speed, motor speed and motor voltage. Okay, motor voltage and motor speed. So if you increase that one, ideally, if you increase the voltage, the speed is going to increase. ideal case. But here it is connected to an oscillator, and there what will happen when it reaches this particular voltage corresponds to omega n. After that, it is not going to, whatever voltage you give, it will get stuck there. It is not going to move further. Maybe what I should say that after this point, actually, I should not draw anything, because here is actually it ends there. It does not change anything. Whatever be the value, but still, this part I think is correct. And for a high voltage, it starts from here, and it should come at this point. But the question is, what happens when when V is less than V naught?
Sir, can we even come from high voltage, sir? Because if we must cross that,
No, not necessarily. I can stop it. So, for example, I can hold it. I can hold this one. Okay. Temporarily, I hold this one. Let the motor run at a very high speed, high voltage, and then release. Isn't it? I can do that.
okay, sir.
Yeah. So just we'll have to check what will happen when posting down, whether it will be like that or what will happen. But posting up, it is very clear that it will go to zero. But what my doubt is that even if the voltage is being decreased to zero, it is getting stuck. So while coming down, it will never be able to reach that situation. That is the thing will happen, and I should not draw anything beyond that, because while coming down, voltage, of course, we can change to zero, but we'll have to see. We'll have to see. I'm not. I'm now a little confused about what is going to happen here while posting down. But posting up, it is very clear. It is not going to actually. It gets stuck at this point. It will never be able to cross the critical speed. Okay, that means it will never be able to cross the resonance. So this kind of phenomena is very interesting phenomena. It's called the Sommerfeld effect. Sommerfeld effect is a little different than that, but still I would like to call it Sommerfeld effect. This is actually because of the non-ideal nature of the source. Non-ideal source. Okay. Actually, there will be always certain damping. Okay, and this happens because there is some resistance. This happens only because of some resistance in the circuit, electrical circuit. I'll talk about it later on in some more details. But what I wanted to say is that here in today's class, that is resonance we talk of, and we say that it will go to infinity and so on. We draw nice curves, and I can write down the equations, etc. But all of them are actually practically become meaningless. Okay, because our preliminary assumption is they are violated. We first assume that the source is ideal source, which they are not. Then we assume that the amplitude or the response level so low that we neglect the nonlinear terms, but in resonance we cannot do that. So in the near resonance, we'll have to modify our model so that the correct physical phenomena can be observed. Okay, so this kind of results, which I am showing it on board, nice curves as omega nt, sine omega nt, all this term is they do not actually occur in practice, because there are many things which we have ignored, but they become important in this. Is this clear to you?
Sir, we have one class. Should I leave?
Yep. Another class.
Sorry, sir, but our class is started for.
Okay, so you may join now your class. You may leave now. Okay, those who want to leave, you may leave. But those who want to stay back and ask me questions, they are welcome. Do you have any question?
Okay, then let us leave. We'll meet again tomorrow and discuss certain other issues. Thank you.
Thank you, sir.